Hi again! In this section we will learn about the helicopter drive system from the engine to the rotor. We will start with the engine Rotax 915IS, which is the engine mounted on our helicopter. It's one of the best engines in the market right now. An Austrian aircraft engine produced by Rotax for use in ultralight aircraft, home-built aircraft, light sport aircraft, small helicopters, and gyroplanes. When it comes to its technical details, Rotax engine 915IS is the proven concept of the Rotax 912 and 914 engine series. A swash plate is a component which can be used to convert circular motion into reciprocating motion and vice versa. It's used by the pilot to adjust the blades of a helicopter in order to achieve lift and control the position of the helicopter. The transmission system transfers power from the engine of the main rotor, tail rotor, and other accessories during normal flight conditions. The main components of the transmission system are the main rotor transmission, tail drive system, clutch, and freewheeling unit. The freewheeling unit or autorotative clutch allows the main rotor transmission to drive the tail rotor drive shaft during autorotation. In case we have the engine RPM is less than the main rotor RPM, the freewheeling automatically disengages the engine from the main rotor. This allows the main rotor to continue turning at normal flight speeds. Helicopters' power transfer function from the engine to the main rotor, tail rotor, and other necessary accessories is performed by the main gearbox, typically known as transition as well. The main purpose of helicopter main gearbox or transmission is to reduce output RPM of the engine to most suitable level for driving the main rotor and tail rotors of helicopters. The rotor system is the rotating part of helicopter which generates lift. The rotor consists of a mast, hub, and rotor blades. The mast is a hollow cylindrical metal shaft which extends upwards from and is driven and sometimes supported by the transmission. At the top of the mast is the attachment point for the rotor blades called the hub. The rotor blades are then attached to the hub by any number of different methods. Main rotor systems are classified according to how the main rotor blades are attached and move relative to the main rotor hub. There are three basic classifications. We have the semi-rigid, the rigid, and the fully articulated. The rigid rotor system is mechanically simple but structurally complex because operating loads must be absorbed in bending rather than through hinges. In this system, the blade roots are rigidly attached to the rotor hub. Rigid rotor systems tend to behave like fully articulated systems through aerodynamics but lack flapping or lead or lag hinges. Instead, the blades accommodate these motions by bending. They cannot flap or lead or lag, but they can be feathered. As advancement in helicopter aerodynamics and materials continue to improve, rigid rotor system may become more common because the system is fundamentally easier to design and offers the best properties of both semi-rigid and fully articulated systems. A semi-rigid rotor system is usually composed of two blades that are rigidly mounted to the main rotor hub. The main rotor hub is free to tilt with respect to the main rotor shaft on what is known as a tethering hinge. This allows the blades to flap together as a unit. As one blade flaps up, the other flaps down. Since there is no vertical drag hinges, lead lag forces are absorbed and mitigated by blade bending. The semi-rigid rotor is also capable of feathering, which means that the pitch angle of the blade changes. This made possible by the feathering hinge. Fully articulated rotor systems allow each blade to lead lag, which means move back and forth in plane, flap, move up and down about an inboard mounted hinge independent of the other blades, and feather, rotate around the pitch axis to change lift. Each of these blade motion is related to the others. Fully articulated rotor systems are found on helicopters with more than 2 main rotor blades. A tail rotor system is designed to stop the helicopter from spinning around when it lifts off the ground. As the engine drives the main rotor in one direction, the fuselage wants to rotate in the opposite direction. This is because of the Newton's third law. For every action, there is an equal and opposite reaction. The tail rotor and anti-torque system creates thrust to push the tail boom in the opposite direction to which it wants to turn from the torque. When the thrust from the anti-torque system matches the torque being created by the main rotor, the helicopter will remain pointing forward when it lifts off the ground. Now, we know what the role of the tail rotor system is. Let's look at the incredible pieces of engineering that prevent today's helicopters from spinning around. This is the most common type of anti-torque system that you will see on a helicopter. It comprises of 2 or more rotor blades that change pitch to adjust the amount of thrust they produce as a unit. The pilot controls the pitch of the tail rotor by pushing on the foot pedals or the anti-torque pedals. Push on the left pedal, it adjusts the pitch and turns the nose of the aircraft to the left. And the same thing happens when you push the right pedal. The pitch either increases and creates more thrust to turn the helicopter against the main rotor direction, or the pitch decreases and allows the torque to pull the nose on the helicopter in the same direction of the main rotor blade's direction. This anti-torque system works by placing a multiple bladed fan within a duct in the tail of the helicopter. The duct is integrated into the tail boom and is usually made of fiberglass skin. The fan consists of between 8 to 18 blades depending on the aircraft model and is of a much smaller diameter than a conventional tail rotor system. Controlling thrust of the fenestron is done the same way as the conventional tail rotor system. The pilot changes the pitch of all the fenestron blades together using the foot pedals in the cockpit. A mechanical and hydraulic linkage connects the two. The fenestron design allows for several improvements over a regular tail rotor. Its smaller tip vortice on the ends of the fan blades help maximize thrust, produced a huge reduction in noise compared to a traditional tail rotor. Shrouded design allows a safer working area for crews with rotors turning and helps minimize tail rotor strikes when landing at unprepared helipads. NOTAR stands for no tail rotor, and it's exactly that. The NOTAR system comprises of an engine-driven variable pitch fan that is mounted perpendicular inside the tail boom to produce large volumes of low-pressure air that exit through horizontal slots along the right-hand side of the tail boom and via a rotatable jet thruster at the end of the tail boom. A power is increased when the collective is raised. The pitch on the fan blades is increased to produce more airflow to counteract the increased torque. The low pressure air released down the length of the tail boom creates a Coanda effect around the tail boom, which acts as a venturi to pull the downwash from the main rotor around the tail boom and exit off the left. This creates an area of low pressure on the right hand side of the tail boom, pulling the entire tail boom to the right, counter-reacting the torque from the main rotor. Just like the Fenestron, the Notar system gives similar improvements over a standard tail rotor. Quietest anti-torque system on any helicopter. No external rotating parts allow for improved working safety around the aircraft or the helicopter. No rotating parts to hit when landing at unprepared helipad.